So yeah, my name is Siyang. I also go by Sean. I'd first like to thank the organizers for the chance to give this talk today. I'm a fifth-year PhD student at Johns Hopkins, and I will be a Brinson Prize Fellow at Berkeley coming this fall. And today I'll be talking about expanding the tip of the red giant branch in the J region asymptotic giant branch type 1a supernovae calibration samples to investigate systematics in the distance ladder. I first wanted to give a shout out to all of the mentors and collaborators that I've interacted with over the past 5 years. Could probably not have done the work I'll be presenting without them, so I'm very grateful to them. And so my work is motivated by the Hubble constant, or H0, which parameterizes the present expansion rate of our universe, as well as sets the age and size scales of our universe. Now, broadly speaking, there are two ways we can take to measure H0. The first is cosmologically, where we take information from the early universe, such as observations of the cosmic microwave background, combined with a model of our universe, such as lambda CDM, and using those to infer the present expansion rate today. The second approach is more locally, or directly, where we take distances to galaxies using an extragalactic distance ladder. I'll be talking about that more later on. Combining those two with the redshifts of those galaxies and using that to measure H0. Now, generally, agreement between these two approaches, cosmological and local, would provide a very powerful end-to-end confirmation of the lambda CDM model used for the cosmological measurements. However, at the moment, there is a larger than 5 sigma difference between these two approaches, and this is what we call the Hubble tension. So on the right here, I'm showing a compilation plot from the recent CosmoVerse white paper that was co-led by Eleanor and Jackson. I know many of you in the audience are co-authors on. On the top here, we're showing the cosmological measurements. In this middle panel here, we're showing the direct measurements. So as you can see, generally, there is a disagreement between these groups of measurements. Now, I do want to note that most of these measurements were performed independently from the Shoes group, for instance. So this was a community effort. So, for instance, there are measurements of H0 using surface brightness fluctuations from John Blakesley, Joe Jensen, Brent Tooley. There's also Julie Fisher from Khalid Saeed and Paula Babel. Geza, who's in the audience today, uses type 2 supernovae to measure H0. There's also Don Pesky, Mazers, Desi Calibration. I'm certainly missing a few, so apologies for that. And so this tension really necessitates intense scrutiny to search for potentially unaccounted for systematics or even new physics. And so the goal of this work will be to develop independent routes to measuring H0 to test the robustness of these measurements, ultimately to investigate the origins of the Hubble tension. I'm sure many of you are familiar with the distance ladder, so I'll just do a very brief recap. In this distance ladder, we create many rungs in order to reach galaxies that are very far away with our standard candles. Our first step is to calibrate the intrinsic luminosities of our candle using geometric distances. We use that information to measure distances to further galaxies that host both type 1a supernovae as well as our candle. We use that to calibrate the intrinsic luminosities of our type 1a supernovae, and then use that and repeat to measure distances further into the Hubble flow. Now, I would say at the moment, the 4 anchor Cepheid type 1a supernovae distance ladder is currently the most mature ladder and yields the highest precision H0. And so it's this distance ladder that we will really want to scrutinize and test. So the overarching objective of the work I'll be presenting is to refine and characterize different ways to measure distances to galaxies as well as H0 independently from the Cepheid-based steps of the distance ladder. This is to cross-check those systematics, and ultimately we also want to leverage the full set of available data that's available publicly in order to increase the leverage of these measurements. And so there are a couple standard candles, as Abby had mentioned in her talk, that can be used to do these cross-checks. One is the tip of the red giant branch, TRGB, and there has been a recent revival of another candle called J region asymptotic giant branch that's based on carbon stars, and Abby gave an introduction to that already. I'll be talking about these two standard candles later on. So I first wanted to talk about the tip of the red giant branch, or the TRGB. And the TRGB refers to the maximum luminosity reached by red giant stars before they transition onto the horizontal branch. So this is an evolutionary feature of stars. And the TRGB manifests as a sudden drop or discontinuity in the number of stars as you go from the bottom to top direction in a color magnitude diagram. Now there are a couple of approaches we can take to identify and measure this TRGB. One of them involves what we call a Sobel filter or an edge detector. So what we do here is we collapse this color magnitude diagram onto the y-axis to create a luminosity function, which is again simply a histogram of the brightnesses or the magnitudes. We can then run a Sobel filter or an edge detector to try to identify the location where the change in slope of this luminosity function is the greatest. And we simply take the maximum response of the Sobel filter as the location of our TRGB. So very recently, we were able to observe 8 different galaxies with the James Webb Space Telescope in the I band, where the TRGB is least sensitive to metallicity. We use these observations to measure TRGB distances, and this really provides an excellent opportunity to cross-check the systematics in the Hubble Space Telescope Cepheid distances, here leveraging the independence of the instrument, so HST versus JWST, as well as independence of the candle, so Cepheids versus TRGB. Now we can see with JWST, the increased resolution really does help clean up the color magnitude diagram quite a bit. We do have a very well-defined Sobel response right here. To make these measurements, we adopt the CATS, or the Comparative Analysis of TRGB measurement algorithms. These are publicly available, so anyone in the audience can access them anytime. And we calibrate our results using the calibration from Deep Anand's paper. And if we simply just take the weighted mean between the differences, or the distances determined using JWST TRGB and HST Cepheids, we do find a difference about 0.0 magnitudes, and really no statistically significance of a systematic or an underestimated systematic in the HST Cepheids that would be large enough to resolve the Hubble tension. Now, of course, one of the limitations of this study is the sample size. Here we only have 8 different galaxies that we're looking at. So one thing that we can do is to maximize the sample size of our TRGB distances in order to increase the statistical leverage we have on our comparisons with Cepheids as well as H0 measurement. And so in this iteration, I had measured distances to 5 different galaxies using data from the HST archive that had not been published before and had already been public for quite a bit of time. And so the goal here was to combine all of the TRGB distances in the literature with these new measurements to really maximize the statistical leverage we have on our comparisons with Cepheids as well as H0 measurements. So what I'm showing here on the left is a plot that from my recent paper that I credit to UK Murakami, the grad student in my group, for designing. These orange dots here represent the individual values of H0 that you would get if you had used one type 1a supernovae calibrated with TRGB to measure H0. Now, as you can see, there's quite a bit of variation. So it goes from maybe 56 to 87. That's perfectly expected. That's dominated by the intrinsic variations of the type 1a supernovae. So we would expect that as we increase the sample size of our type 1a supernovae, we would tend to go towards reversion to the mean. But that also means, conversely, if we do have a smaller sample size, we're also more susceptible to changes or fluctuations due to low number statistics. And so you might notice that these little orange dots are also inside these larger circles, like right here. That kind of represents the different programs that have been conducted in the past. And of course, not all those programs had included the full sample of type 1a supernovae. And so that's what we aim to do here. So in the bottom plot here, I'm showing a histogram, again, of all these individual type 1 values of H0. Here we're now labeling each of these squares with the name of the type 1a supernovae. We can see with the expanded sample of 35 type 1a supernovae, the distribution is, maybe we can approximate it as roughly Gaussian. That's shown here with the black. And if you had taken a mean of the H0 values, you would get somewhere around 71, 72. And that's what we find. We find H0 is 72.1 when we use the entire sample. Now we can compare that to some of the values measured in the literature. So for instance, if we had selected the subsample of type 1a supernovae used by the CCHB team, that's shown here in the pink, we do actually get a lower H0, lower than the mean of when we use the entire sample, and that's perfectly expected. We do have a lower sample size in that case, and that tends to shift the mean value of H0 by a little bit. Conversely, you can also see that if we had looked at the 11 type 1a supernovae that were excluded by the CCHB analysis, that would yield an H0 that's much higher, almost closer to 75, and that's of course higher than the mean as if you had used the entire sample of type 1a supernovae. And if you have combined those two samples, the 11 excluded and the 24 other type 1a supernovae, you would get something in the center. And so we did also explore different measurement variants or subsample variants, where we selected different subsamples of our type 1a supernovae and looked to see how that changed our results. And in particular, we were also able to reproduce the H0 value from the CCHB team simply through subsample selection, as well as applying particular choices like neglecting peculiar velocity corrections. And so I would say with the results of this study is that once we include the full sample of type 1a supernovae, not throwing out any of the public data that's available, really the H0 that we get has no evidence of a significant systematic in the Cepheid-based H0. That would be enough to resolve the Hubble tension. So I now wanted to move on to the J region asymptotic giant branch, or the JGB. And so Abby gave an excellent introduction to this, so I'll be very quick. The JGB refers to this overdensity, or this clump of stars, as shown here in a near-infrared color magnitude diagram that contains thermally pulsating carbon-rich asymptotic giant branch stars. And it's been proposed in the literature that some sort of mean or a median or a mode magnitude of the stars in this J region can be used as a standard candle. Now, the argument for why we can do this lies in the expectation that a star has to have a mass that lies within a relatively narrow mass range in order for that star to become a carbon star in the first place. If it's too massive, bottom burning will occur and carbon will be burned before it reaches the surface of the star. And if there's not enough mass, the third derivative events are too insufficient to bring enough carbon to the surface. So essentially, you need a mass that's just right in order for that star to be in that region in the first place. And of course, that constrained mass range then translates to a constrained luminosity range. Now, I will note that this is actually not the entire picture, and I'll be talking about that more later on. So the JGB does have several advantages, including that it requires only a single epoch to observe, and that's in contrast to maybe Cepheids, which require about a dozen to constrain their periods. In addition, the JGB has the potential to reach further than both the TRGB and Cepheids. Now, for the TRGB, the JGB is about 1 to 2 magnitudes brighter. And for Cepheids, well, Cepheid amplitudes decrease with redder wavelengths, and that makes discovering new Cepheids with the James Webb Space Telescope extremely difficult, because their amplitudes become similar in size with photometric uncertainties. Now, we can potentially reach maybe around 50 megaparsecs with the JGB with about a 5,000 second exposure time. That allows one to double the type 1a supernova calibration set to decrease statistical uncertainties in that calibration by about 30%. But also, two, very importantly, is to measure H0 independently using galaxies not reached with Cepheids before. Now, we were able to observe this J region in our JWST program 1685 during cycle 1 led by Adam Rees, which had targeted the maser host NGC 4258, which we'll use to calibrate the intrinsic luminosities of our candle, as well as 4 galaxies that had hosted type 1a supernovae. Now, as I mentioned, the JGB was recently revived. It does seem to be very promising as a new standard candle based on the literature, but how standard is it as used at the moment? I'll be checking this. There have been several methods proposed to measure the JGB reference magnitude. This includes the mean, the mode, the median, or model fit. I'll be exploring many of these. And finally, I'll be comparing distances to our galaxies using the JGB and comparing those to distances derived using Cepheids, tip of the red giant branch, and Miras, all calibrated to the same anchor galaxy. So here I'm showing the footprints for our observations. Again, 5 different galaxies, including the maser host NGC 4258. Oops. What we're going to do here is we're going to measure the JGB using stars inside these boxes, but also outside these red ellipses to kind of best estimate the outer disk. Now, I will note that in the outer disk, of course, as has been mentioned in the last talk, there is crowding, meaning there's nearby stars that will contaminate your photometric measurements. And so although in the outer disk the crowding is reduced, it is still non-negligible at an order of a few hundredths of a magnitude. And so how we typically correct for this is we use artificial star tests, and I do have backup slides if you're interested in learning more about that, but essentially here we also develop an artificial star test pipeline to correct for this bias in a statistical sense, in a population-based sense, to ensure that our measurements are not biased in the brightwards direction. Just a quick note, we do also make sure to apply foreground extinction corrections via the Schlafly and Finkbeiner dust maps. So I wanted to very briefly introduce how we're going to measure the JGB. What's typically done is we first want to isolate the J region. We do this by placing a box in the color magnitude diagram. This involves a series of magnitude and color cuts, as shown here. And as I mentioned before, there are several methods that can be used to measure the JGB. And really all of these seek to identify some sort of peak in the J region luminosity function. This can involve the mode of a smoothed and binned luminosity function, which is pioneered by Abby. Can take the mean or median magnitude of those stars. You can fit a model, or you can use other alternative definitions of the median. In particular, in comparison with TRGB, we're essentially trying to find the average brightness of these stars in the J region. And that's conceptually much simpler than, for instance, the TRGB, where we're trying to identify this discontinuity. Now, because a priori, we don't really know which of these measurement methods really best reflects the standard nature of the JGB, we decide to explore several measurement variants in order to explore how these different choices really affect our measurements. So we look at a total of 25 different combinations of how to measure the JGB. This includes 5 different color ranges as well as 5 different summary measures, including the mean, median, mode, and a co-model fits. In particular, we have 2 different strengths of smoothing for the mode method. And I'd also look at changing the binning, although I found that that made very little difference. So one of the first questions I wanted to ask was, how standard is the JGB? And one excellent way to do this is to look at the field-to-field variations of this candle. So we would expect that for a properly standardized candle, the magnitude of that candle should not vary significantly depending on where you look. Of course, it's in the accepted region, like the outer disk for the JGB, because the distance to the galaxy, of course, is fixed. Now, we performed a series of null tests. This is one of them. We looked at NGC 4258. And here we have 2 different fields that lie on opposite sides of a galaxy. And what we can do here is simply measure the JGB using stars in the field right here in the B module, measure the JGB using stars here in the A module, and then compare the difference. So here on the right side, I'm showing the results. On the y-axis, we're showing the difference between the JGB measurements in those 2 fields, plotted as a function of the measurement variance. Again, 25 different measurement variants. And so perfect agreement here would be consistent with 0. But we find that most of the measurement variants are in fact not quite consistent with 0, and this does seem to hint at some sort of intrinsic variations. Now you might have noticed too that the JHB measurement also does change depending on which statistic you adopt, mean, median, mode. And this is because there is non-uniform asymmetry in the J region luminosity function, which inevitably causes differences between measurement methods. In other words, if your luminosity function is symmetric, your mean will agree with your median and your mode, but if it's asymmetric, your mean will be different from your median and your mode. And that means your JG measurement will also change depending on which statistic you adopt. Now, for instance, in NGC 4258, we found that the difference between the mode and the mean JGB was almost 3/10 of a magnitude, and we did also see non-zero differences in our type 1a supernovae hosts, although to a lesser extent. Now, we also sought to see if this persisted in the ground-based data for the Large Magellanic Cloud and the Small Magellanic Cloud. What we did here is we measured the JGB in these 2 galaxies in both the J and the H bands. We took the difference between those magnitudes, and we compared that to the difference in the geometric distances to those galaxies determined via detached eclipsing binaries, or DEBs. And ideally, if the JHB were standardized in this case, they would agree very well with the geometric distances. But as we see here, most of these measurement variants don't quite agree with the geometric distances shown here on in the shaded region, except for maybe the mean. And so that's something that really needs to be looked into for those ground-based studies. So the next thing that we did was to measure distances to our galaxies, and we're going to compare them to the distances in the literature. So here's just a summary plot from our first iteration on the right. On the y-axis, we're showing the difference between the JWST and the Cepheid measurements. This is across many different galaxies, and so we just simply take the median. Again, this is plotted as a function of the 25 different variants. And the red line shows kind of the median of the differences out of all these 25 values. And so I would say we do find broad agreements with Cepheids, TRGB, and Miras, but there's still this methodological variation that spans almost 2/10 of a magnitude. And this arises due to the unequal asymmetry of the J region luminosity function. And this would yield the larger systematic in an H0 measurement. And so we decided to incorporate these variations into our measurement to find roughly 74.7, but really with a full range spanning 71 to 78, depending on which statistic is adopted. Now we can take this one step forward and do the same thing as we did with the TRGB and try to maximize our JGB sample to increase the leverage we have on our comparisons in H0. And so in the second iteration, we had looked at 6 different galaxies across cycles 1 and 2 from JWST. In particular, these galaxies also have distances that reach almost 40 megaparsecs, which would be the furthest distance observed with JGB. And so the goals here are to, one, test and extend the range of the JGB, but also to compile all the literature values with the new measurements here to really maximize the leverage we have on our cross-checks with Cepheids. So on the left here, I'm showing an example of one of the distances that we find. Again, we have distances plotted on the left, on the y-axis, plotted as a function of the 25 variants. Show the Cepheid distance in blue for reference, as well as the TRGB distance in orange. Red, the red line here, horizontal line, shows the median distance out of all the 25 variants. So similar to our first iteration, we do find broad agreement within the uncertainties with Cepheids and TRGB distances, but these methodological variations persist, and this is something that really limits the precision of the JGB. And so I will note that the 2 galaxies that lie at about 40 megaparsecs, I did see evidence of incompleteness. And so I was able to correct for this effect for NGC 5468s, but for 3147, there was limited signal to noise, and so I was not able to do that. So if you're interested, I could talk about that more. And so now with this expanded set, combining all the literature values together with this new data set, we have 15 galaxies hosting 18 type 1a supernovae. And if we simply, again, take a weighted mean between the Cepheid distances and the JHB distances, we find a difference of about 0.03 magnitudes, really no statistically significant difference between the two. And so with the full sample of our JHB measurements, we do find an H0 of roughly 73.3. And again, this was very good agreement with the Cepheid-based H0 measurement. And so you might have noticed that there have been different values and measurements of H0 in the past. And so I would say that these variations can really be explained by subsample selection. Now on the left here, I'm showing a similar plot to what I'd showed with the TRGB, a histogram of the individual values of H0s using individual type 1a supernovae. In the pink here, we're showing the galaxies that were observed by the GEO 1995 program. And we see that individually they contain supernovae that naturally have a lowered H0s, on the left side of this distribution of full type 1a supernovae. Now, if you had included the full sample, which are shown here, the brick red or the darker red, we do see that that does tend to pull H0 a little higher because, of course, you have a better statistics and a reversion to the mean. Of course, this doesn't mean that any of these measurements are wrong or done incorrectly, but it's simply the fact that there is these intrinsic variations in the type 1a supernovae that then translate into fluctuations in the H0 measurements. Now this can also be seen that this is expected even with the Cepheid distances. So on the right here I'm showing the same plot, same histogram, but now using Cepheids to calibrate the type 1a supernovae. And we see that there is a similar trend. In the light blue, the type 1a supernovae from the GEO 1995 program do tend to lie on the lower H0 side. But of course, if you had included the full sample that's available, that would yield an H0 that's a little higher. And so one of the questions that you might have is, where does this asymmetry in the luminosity come from? I think I'm running out of time, so I'll try to go through this very quickly. This asymmetry was actually also noted by other studies independent from ours. There is the Parada papers, for instance, which had attributed this to metallicity and star formation histories. Abby did an excellent study on the metallicity of the JGB. The scope of it was a little limited in a range of 0.08 dex, but I'm certain there's a lot of potential to improve there. There is also a spectral diversity of stars in the J region, and the fact that not all stars in the J region are actually of the same type. So are these different carbon star types, these J types and the N types, that live in the J region? And if we had simply plotted the luminosity functions here, separated out by these J types and these N types, we see that they have means that are quite inconsistent with each other. You can certainly see that if we had combined the blue and the black histograms, we'd certainly get an asymmetric luminosity function. And so another consideration is that there is a slope in the J region. And so when this method was first developed, it was assumed that the mean magnitude of these carbon stars would not have any significant variation with color, or the x-axis in this diagram. But as we have more and more data, we are seeing that there is a significant slope. So for instance, I'm showing two fields for NGC 4258 here on the bottom. On the left here, if we simply plot a line through these J region stars, we do see that there is a slope with about 7 sigma significance. In the same galaxy, but a different field, there is still also a slope that has non-negligible difference or significance, but the slopes are actually quite inconsistent with each other. And so this is something that we actually do try to incorporate into our systematic uncertainty via these measurement variants and these different choices in color ranges. And so just to wrap up, in the works that I presented, we really tried to investigate systematics and the Cepheid-based steps of the distance ladder by using these alternative standard candles, tip at the red giant branch and the J region asymptotic giant branch. Now, we produced new measurements of the TRGB with the James Webb Space Telescope. We also leveraged all the available data that's publicly, that's available on the archive. And anyone in this room can also access that data, both the raw data and also the photometry that we used here. The JGB, we also standardized and really tried to characterize, tried to characterize the JGB, the systematic uncertainties there. We do see at the moment there is potential to improve, and I think this is natural given, of course, the relatively new age of this method. There's still a lot of potential for the candle, but I just think there's much more work to be done. But still, if within those uncertainties, we do find excellent agreement with the Cepheid-based distances and H0. And again, in here, we also then leveraged the full sample size, all the data available in the literature. We really find that there's no really reason to exclude a particular set of type 1a supernovae given those intrinsic fluctuations, now that all that data is public. And so I would say that these results do support the Cepheid-based distance ladder. We don't find any evidence of a significant systematic that would be enough to solve the Hubble tension. We do see that we do have a much clearer picture of the systematics and have a much better leverage on these comparisons and H0 measurements if we do, again, leverage the full power of the public data that's currently available. So I'd like to thank you for your attention. I can take any questions.
So I'd like to ask regarding the symmetry or the asymmetry of the distribution. Have you thought of using that to sort of standardize the JGB as a candle?
Yeah, so thanks for asking that. So yes, we did try to use the skew of the luminosity function. Yeah. And when we plotted that as like the distance or we didn't unfortunately find a correlation. So that's something that we have looked into, but I think there's variations that we still don't understand fully. And so unfortunately, we just can't use the skew of the luminosity function just yet.
But there might be other statistics of the asymmetry.
Yeah, definitely. Potentially.
Thank you, Sean. Nice talk. Actually, a question to both yours and Abby's presentation, because for a person not working actively in this field, it looks a bit messy. The story about defining a band or a tip, right? It looks like inevitably there are choices, which so I wonder, isn't there a discussion in your community about how to do that better? And sort of follow-up question: are there mock data sets from just stellar populations where you create a mock data set with all kinds of stars, and then you try to figure out whether your method picks the right thing with the right error? Or I don't know, just for discussion.
Mm-hmm. Yeah, thanks for asking that. And of course, Abby's welcome to chime in. And so, yes, I do agree that the method and the selection is very messy. And so that is one of the reasons why we do decide to look at measurement variance. And because really a priori, we don't really know what is the perfect magnitude cuts, what is the perfect color cuts. We don't know which statistic really does best represents, the mean magnitude or the median magnitude of these stars, or the standardization of these stars. And so as a first step, we do try to then just look at measurement variance, characterize the changes in these measurement choices, and adopt an uncertainty based on that. But the next step that I do think would be worth looking into is to really understand why are these intrinsic variations, better understand the diversity of stars in the J region, and then use that as a way to better understand which method then do we choose. For instance, that can then, inform us what is the proper color cut, what is the magnitude cut. Do we use the mean, median, or mode, depending on what combination of populations we have in there. And I think that is a next step that we can definitely take. But here, I think it's still very important to still characterize and be aware of these differences in the methodological choices, but also intrinsic variations, and at least build that into the uncertainties so that people, you have a more realistic estimate of H0 and also your comparisons with Cepheids. And Abby, if you have any input, you're welcome to chime in. And then your second question was, can you remind me really quick?
Yeah, there are mock data sets where you do, somebody creates a synthetic data set of all kinds of stars, right? And
right.
In a color magnitude diagram, and then you use your method and you figure out. You don't know, priori. Somebody knows which stars are which, but you don't know. And find out whether you pick the right, tip or band, whatever.
Right, and so yeah, that's a good point. And I think so. It is difficult. So there are certainly, mock data sets that we can use for simple stellar population, for instance, and maybe combine those. But ultimately, I would say that at the moment we don't have enough information to know for each galaxy what is the, for instance, fraction of these, J-type carbon stars, these extrinsic carbon stars, or these N-type carbon stars, for instance. And so that is one approach that we can take. We can maybe do a grid search, look through a possibility of many different combinations of these stars. There's certainly actually evidence of actually non-carbon stars that are also in the J region as well. And so that is certainly, I think, maybe with taking spectra first of the stars in the J region, identify the diversity in there, and then start creating mock catalogs to kind of simulate this on a galaxy-to-galaxy basis. It's certainly something that can be done.
Yeah, I can also respond to that. I think Sean is right. There's still a lot of work to be done, but I think that's why I advocated for kind of testing in this nearby regime, because the goal is we want them to be as accurate as TRGB and Cepheids, and so that's why I really tried to measure distances to galaxies where the TRGB and Cepheids agreed, and that's how we developed the method. So that's why we chose the mode, because we noticed that's when the JGB distances agreed best with Cepheids and TRGB and the nearby, closer than 5 megaparsec galaxies. So I think that when you're developing the method, you want to be doing it in these closer galaxies and make these choices, and that's when you apply it to the farther galaxies. The fact that the mean, median, and mode don't agree is interesting, but I don't think that necessarily makes it a bad standard candle.
Mm-hmm. Yeah, definitely. And so, yeah, I think that's a really good point. And so could you also help clarify to the audience, how do these nearby distances help elucidate the population differences in the J region?
Yes, I don't know if I understood correctly, but when you showed the supernovae that were not included, so I'm a bit worried that there may be data bleeding, because basically you know the answer, then you're going to cut on the cases for which you have larger value or outliers, and then you redo the analysis. So this is statistical learning is called data bleeding, and this is something that must be avoided. So can you please comment on that, because I think this is a crucial point.
Yeah, certainly. And so in our study, we do certainly try to include all 35 to avoid any of that selection bias. And so that's why everything that's available publicly in the literature we choose. Now, there are certain studies out there that do select a subsample of galaxies, and I'm not part of those teams, so I can't comment on what their selection criteria are. It is, it could be, by chance. It could also be because at that time we didn't have enough data, so people just selected subsamples as we got more data coming in. But I think at this point, really, with this full sample of 35 type 1a supernovae, it is important to include everything. And so even if we do know the individual values of H0, we're not selecting anything. And so there's no, choice, or there's no, room for, doing this, introducing that bias or that selection bias.
Yes, thanks.
Right, so the subjective kind of elements have come up a couple times, and I just wanted to ask, can you explain a little bit, so what is your process for the artificial star tests, and how does that affect inner versus outer disk? I'm trying to understand how the methods differ in that regard, and how well you can perform with these artificial star tests.
So yeah, as you look and perform photometry on these stars in a crowded region, you do get contamination and flux from nearby sources, and this will make and push your H0 or your magnitude measurement in the brighter direction. And so what we do here is we correct for this in a statistical manner. So we place artificial stars, which are fake stars generated by the Dulfalt software, our photometry suite. We know the input magnitude because they're fake. We then put them in the image, we recover them with our photometric pipeline, and then look at what the difference is between that input and output magnitude. And we do this for many, many different stars. We place the stars also randomly in certain regions. And what this creates is a histogram of the differences of the different magnitudes. And so essentially what we do is we can take the mean magnitude of this distribution. What this does is then corrects for this bias in a statistical sense. It does not correct for the scatter in the Cepheid relation or the JHB relation. And so in that way we are essentially correcting for this contamination from flux from nearby stars. It doesn't necessarily reduce our uncertainties. If anything, it does increase the uncertainties by a tiny bit, maybe estimated by the widths of this distribution. But again, we are trying to correct for that bias. And so for the JHB in particular, since we are in the outer disk, this crowding bias is non-negligible. It's still order of a few hundredths of a magnitude up to 500ths of a magnitude, something that we do need to correct for. It is a little more difficult because we are looking at population-based stars. For Cepheids, you can correct for this on a star-by-star basis. But here we now, what I had to develop was a grid-based approach. We measure or estimate the crowding bias in a particular grid or a particular region in our image, do that for many, many instances across the image, and interpolate by magnitude as well, and then apply that correction to our JGB stars. And so I hope that answered your question.
Thank you very much, and we really need to close this talk. Thank you so much again for